In this video, I'm going to give two simple examples of sizing a solar system. I see this question asked a lot. Something like, how much solar do I need for a typical 4-bedroom house? Or, I just need my computer, some lights, and a refrigerator. What's the smallest system I can get away with? And these questions are answered a lot, too. There's probably dozens of YouTube videos. But I watched some of them, and I noticed the answers get pretty complicated. So I thought I would make a video showing how to do it as simple as possible. I think people are looking for quick and dirty, back-of-the-envelope kind of calculations. And that's what I'm hoping to give here. It may leave some stuff out, but we can always get a little more complicated later on. This will give us a great starting point. So let's see how easy we can make it. There is going to be some math, so grab a calculator, but it's really just some simple addition, maybe a little multiplication or division. Nothing too complicated. My name is Joe. I bought 5 acres of raw land in the high deserts of Arizona, and I am building an off-grid homestead. Welcome to my channel, Off-Grid Solitude. So let's dive right in. There's a couple things we need to know first. Electricity is measured in watts. Watts measures power. The more watts an electric saw has, the stronger and faster it is. The more watts an electric oven has, the hotter it is. We multiply watts by hours to get watt hours. Crazy, right? Watt hours is the total amount of energy used. And we talk about watt hours when we talk about how much energy we use in a day, or how much energy our battery bank holds. Another thing, just to make it complicated, they sometimes talk about kilowatts and kilowatt hours. Now a kilowatt is just 1,000 watts. So we can multiply or divide by 1,000 to convert between the two. For some reason they think that makes it easier. The first part of this process is figuring out how much electricity we use in a day. The first example will be our friend Jim. Jim lives in an apartment, so this is going to be really easy for him. He can just look at his electric bill. Every electric bill is a little bit different, but they all usually show average daily use, and they usually have a chart that shows every month of the year, assuming you've been there for a full year. Most people use more electricity in the summer because of air conditioning, and Jim does too. But depending on where you live and what you're doing, sometimes it can be more in the winter, especially if you use electricity for heat. To make sure he always has enough electricity, we're going to work off that biggest month. And in this case, we can see Jim uses about 3.8 kilowatt hours per day, or 3,800 watt hours. So that sure was easy, wasn't it? In this second example, Tom doesn't have an electric bill. So we're going to have to make some estimates and add it up for ourselves. So Tom listed all the things he can think of that uses electricity. He's got a refrigerator, a microwave, a coffee maker, and a slow cooker in his kitchen. He's got a computer and his Wi-Fi router. He counted 4 lights in the various places in his cabin. And he figures he might want some AC in the summer. So it's pretty easy. We're just going to list out all these items and figure out how much electricity each one uses. For the refrigerator, we can look at one of those energy efficient rating sheets. They give a yearly energy usage. So we can just divide by 365 days per year and get our daily usage. In this case, we see 547 kilowatt hours per year. Divide that by 365. And remember, kilowatts is 1,000 watts. So we get 1498 watt hours per day. The microwave says it's 1100 watts. So all we need to do is figure out how long we're going to use it each day. You usually only use a microwave 5 and 10 minutes at a time, but you can use it a couple times a day. So let's say it gets used for half an hour a day. So 1100 watts times 0.5 hours gives us 550 watt hours. Similar with the coffee maker. I looked it up on Amazon, which usually tells you what its wattage is. It says 650 watts. It takes about 15 minutes to brew a pot of coffee. So that's 650 times 0.25, 162.5 watt hours. Slow cooker uses only about 200 watts, but they cook for a long time, sometimes over 8 hours. So 200 times 8 hours, 1600 watts. I don't know if somebody uses a slow cooker every single day, but just to be safe and be sure we have enough electricity, let's say it is used every single day. The computer is 300 watts and the Wi-Fi is 100 watts. A rule of thumb for things that have a sleep mode or a thermostat which turns it on and off is that they're usually on for about a third of the time. So 24 hours in a day, a third of that is 8 hours. Let's use 8 hours as our base. So 300 times 8 is 2400. 100 times 8 is 800. With efficient LED lights, they each only use about 15 watts. And how long is a light going to be on? Only when it's dark. So let's say 8 hours a day again. So 4 lights at 15 watts each. That's 60 watts. So 60 times 8 hours a day, that's 480 watts. A small window AC unit can use about 500 watts. Again, using our rule of thumb, it'll be on for about 8 hours a day. So that's about 4,000 watt hours. So we can add up all those totals and see what we get. And that'll give us his daily average. Now, for things that aren't used every single day, like power tools, for example, there might be enough cushion to run them without including them in this list because, we did round up a little bit. Or just plan on using a generator for those special items. And this was just a quick brainstorm for an example. But it might be a good idea to do this exercise a couple times just to make sure you didn't miss anything. Off the top of my head, I can imagine a well pump I don't see on this list. You probably might want one of those. But that's great. Now that we know how much each person needs each day, we can figure out how many panels we need to cover that. We'll start by taking that average daily usage and we'll multiply by 1.25. This is just a little cushion to cover inefficiencies. Charge controllers and inverters, none of them are 100% efficient. Sometimes there are some line losses from the wiring, as well as dust on the panels, and the sun doesn't stay put during the day, so unless those panels are moving, they're not going to be perfectly aimed at the sun all the time. So this extra 25% should cover all of that. We'll grab a map or a chart and look up how many peak sun hours our location gets in a day. Sunny Arizona gets a lot more than cloudy New England. You're obviously going to need more panels in one place than the other. But one thing I wanted to point out is you'll notice this map says it's average peak sun hours. You're going to get more sun in the summer than the average and less in the winter. So we want to adjust for that to make sure we don't run out in the winter. Think about what the winters are like where we are. If winters are relatively sunny, you can say it's about 75% of those average sun hours. If winter seems stormy and very cloudy, then you'll probably only get about 50% of your average. So we're going to include that too. So for Jim's example, we saw he uses about 3,800 watts a day. We take that 3,800 watts in daily electrical usage. and we multiply it by that efficiency factor of 1.25, and that gives us a total watt hour of 4750. From the chart, we saw that the average sun hours in Arizona is 6.5. Arizona is a very sunny place with nice winters, so we'll multiply by 75% for the winter factor, and that gives us 4.9 sun hours. So 4750 watt hours divided by 4.9 sun hours gives us 974 watts. Now Jim has decided to use a 100-watt panel that you can buy off of Amazon and some stores. So we take the total watts of 974 divided by 100 watts per panel, and it gives us just about 10 panels he's going to need. Now Tom lives in New England. Not that much sun in New England. This map says about 4.5 peak solar hours. And he says it's pretty stormy during the winter, so we're going to multiply by 50%. We take the daily usage of 11,490, multiply it by that efficiency factor of 1.25, giving us 14,362. We looked up the average sun hours is 4.5, but the winter factor is going to be 50%. So that gives us only 2.3 sun hours. So we take 14,362 watt hours divided by 2.3 sun hours, giving total watts of 6,383. Tom bought larger panels that are 250 watts each. So we take the total watts of 6,383 divided by 250 watts per panel, and we come up with just about 26 panels. Now the last part is to figure out how many batteries you need. Solar panels only make electricity when the sun is shining. So if you didn't have any batteries, you would only have power in the sunshine. And when you use batteries, you can actually draw more power than your panels are producing because the batteries stored them up for you. For example, an 1100 watt microwave, if you don't have 1100 watts of panels, you couldn't run your microwave directly. But you can store some extra energy in the batteries and you will be able to run it. Jim had a daily usage of 4750 watts. Remember, that included that 25% extra padding we put for inefficiencies. Since the weather is so nice in Arizona, Jim figures it's sunny just about every day, so he only needs 1 day's worth of storage. He bought some 100 amp hour batteries. To convert amp hours to watt hours, you just multiply by the voltage. So 100 amp hours times 12 volts gives 1200 watt hours per battery. The total watt hours of 4750 divided by 1200 watt hours per battery gives a total of 4 batteries. Tom needs 14,362 watt hours per day, and again that's including that extra 25% for inefficiency. But the weather is pretty bad where Tom lives. Lots of cloudy days, so he figures he wants 2 days worth of storage. So his daily usage times 2 gives 28,724 total watt hours. Tom found some bigger batteries. He has some 200 amp hour 24 volt batteries. So 200 amp hours multiplied by 24 volts gives 4,800 watt hours per battery. His total energy he needs to store of 28,724 divided by 4,800 per battery gives 6 batteries. So there you go. It was a little bit of math, but nothing too complicated, right? And now we have a really solid basis for the size of the solar electric system they both need. Of course, there were a lot of quick guesses and estimates. So if these numbers we come up with don't seem quite right, or they're too big or too small, we can go back and adjust them a little bit. Maybe we can do without an air conditioner. Or maybe we're afraid we forgot some stuff, so we just want to pad those numbers a little bit, make sure we don't run out. Nature is always unpredictable, and that includes weather and sunlight too. So it's very important to have a backup generator. It depends how comfortable you are using this backup generator. If you're comfortable using it, maybe it'll just be for emergencies, or maybe you're going to hardwire this backup generator into your system, then you can be pretty conservative with estimating your solar system size. But if you don't like using a generator, then it might be better to bump up your system size to make sure you don't run out of power as often. Well, thanks for watching. I hope this was helpful for you. Please consider liking, commenting, and subscribing. It really helps. And I'll see you in the next video.